A cylindrical drill with a radius of 5 centimeters is used to bore a hole through the center of a sphere with a radius of 7 centimeters. We want to find the volume of the ring-shaped solid that remains. Let's first look at this graphically. If we graph the sphere where the center is at the origin, it would be graphed here in blue. Again, the sphere has a radius of 7 centimeters. If we drill through the center with a drill bit that has a radius of 5 centimeters, we would remove the volume inside the red cylinder that has a radius of 5 centimeters. I also graphed the xy plane in yellow because remember, if we set up a double integral and the function f of x comma y is non-negative over the area in the xy plane, it would give us the volume divided by the surface in the xy plane. So now if we look down on the xy plane, notice how if we integrated f of x comma y, which gave us the non-negative part of the sphere over this region between a circle with a radius of 5 centimeters from the drill bit and a circle with a radius of 7 centimeters from the sphere, we can determine the volume above the xy plane. Then if we multiply this by 2 because of the symmetry, we can find all the volume that would be left after drilling through the sphere with a drill bit with a radius of 5 centimeters. So going back to our work, the equation of a sphere with a radius of 7 centimeters centered at the origin would be x squared plus y squared plus z squared is equal to 7 squared, or 49. So if we solve this for z, we can determine f of x comma y, which we can then convert to a polar function in the form f of r comma theta. So solving for z squared first, we'd have z squared equals 49 minus x squared minus y squared. And now we would take the square root of both sides of the equation, which would give us z equals plus or minus the square root of, I'm going to write this as 49, and then instead of minus x squared minus y squared, I'm going to write minus the quantity x squared plus y squared. Notice how here z is both positive and negative, but because we want the part that's only non-negative, we're going to let f of x comma y be equal to the positive square root of 49 minus the quantity x squared plus y squared. So now we need to find our function f of r comma theta. Well, f of r comma theta would be equal to the square root of 49 minus r squared, because remember, r squared is equal to x squared plus y squared. Now let's work on setting up our double integral in polar form to find the volume. The volume above the xy plane would be equal to the double integral of f of r comma theta, which we now know is a square root of 49 minus r squared. And remember, for polar form, we have r dr d theta. And now we need to find the limits of integration for r and theta that would trace out this area in the xy plane. Well, notice r starts at 5 and goes out to 7, which give us the limits of integration for r. We integrate with respect to r from 5 to 7. And then to trace out this area, we need to rotate 1 full revolution, which means we integrate with respect to theta from 0 all the way around to 2 pi radians. Now this only gives us the volume above the xy plane, so we have to multiply by 2 in order to get the total volume that remains after drilling through the sphere with the drill bit with a radius of 5 centimeters. So don't forget, we do have to multiply by 2 to get the total volume. Without the 2, we only get the volume above the xy plane. Now let's go and evaluate this on the next slide. Notice how to find the antiderivative with respect to r. We'll have to perform u substitution. We'll have u equals 49 minus r squared, so differential u is equal to negative 2r dr. Because we have r dr here, let's go ahead and divide both sides by negative 2. So we know that negative 1/2 differential u is equal to r dr. Now to help us find the antiderivative, let's write all of this in terms of u. So we'd have u to the 1/2 for the square root of 49 minus r squared. And then for our dr, we have negative 1/2 differential u. So notice how to find the antiderivative with respect to u, we'd have negative 1/2 times u to the 3/2 divided by 3/2, or times 2/3. Which means, with respect to r, we would have negative 1/2 times, not u to the 3/2, but 49 minus r squared to the 3/2. Then instead of dividing by 3/2, let's multiply by 2/3. Notice how this simplifies here. So we have negative 1/3. We have a 2 here, so let's go ahead and write this as negative 2/3 times the integral from 0 to 2 pi. And then we just have the quantity 49 minus r squared to the 3/2, which we need to evaluate at 7, then 5, and then find the difference. So we'd have negative 2/3 times the integral from 0 to 2 pi of, notice when r is 7, we have the quantity 49 minus 7 squared to the 3/2 minus, when r is 5, we have 49 minus 5 squared to the 3/2. So simplifying, we have negative 2/3 times the integral from 0 to 2 pi of, well, here we're going to have 49 minus 49 to the 3/2, that's 0. And then we have minus, this would be 49 minus 25, that's 24 to the 3/2. So because of the minus, we have negative 24 raised to the power of 3/2. But a negative times a negative is positive. Positive 2/3 times positive square root 24 to the 3/2 times the integral from 0 to 2 pi of d theta, or 1 d theta if we want. So we have 2/3 times 24 to the 3/2 times the antiderivative of 1 with respect to theta would be theta. So finally we have 2/3 times 24 to the 3/2 times, we'd have 2 pi minus 0, which we can write as 4 pi divided by 3 times 24 to the 3/2. Now we could simplify 24 to the 3/2, but I'm going to go and leave it in this form and also get our decimal approximation for the volume. So we have 4 pi divided by 3 and then times 24 raised to the power of 3/2, which should be approximately 492.4991. And because the radius was in centimeters, the volume would be cubic centimeters. So going back to our graph one last time, we just found the volume that would remain if we had this sphere with a radius of 7 centimeters and drilled through the center with a drill bit with a radius of 5 centimeters. So we found the volume of the sphere that is outside the cylinder graphed in red. I hope you found this helpful.